So thank you again for inviting me. This is a topic that I really like and that I always like to talk about. It's something that I've been doing for some years now. It's about how to secure positioning. So I'm really super excited about anything that relates to the physical world. So how do we secure any kind of measurements that that can determine, for example, where we are, or even any other sensing modalities, right? And so why do I care about this? Well, I care about this because obviously this motivational slide will not surprise anyone, but in all these examples that you see here, somehow location or distance information plays a role. So, and these are all more or less critical systems, depends on how much you believe that your pacemaker is a critical system, right? So, for example, in a scenario here where you have cars moving around, and if they are self-driving cars, you might want to know where they are, or they might want to know securely where they are, and also they might want to know their distance securely. In cases like flying drones, you would also like the drones to know their mutual distances securely and to coordinate their flight. In case of access to cars, I will give this example. Actually, there are systems today where you approach a car and the car will unlock if you're close to the car. So this immediately essentially shows you that the notion of proximity or distance is linked to the notion to security, right? So because you derive security notions from distance information. And there are many other examples, right? For example, I could say, well, whoever is in this room gets access to Wi-Fi or gets access to some sensitive data. And this would be a really cool feature because somehow physical access control is very, very natural to all of us. You could define policies like if someone enters my house, they can see a set of pictures that I took from my vacations, right? So, so why is this? So what are the basic kind of security properties that you want out of a positioning system? So what you want is primarily spoofing resilience. So this is a case of GPS, right? Where you want to have your own device, so a device that wants to determine its own location, determine actually a correct location in the presence of an adversary that's trying to influence this location. However, you can have other scenarios, like I want to, for example, know where my kids are. I want to know this securely because they might not want to tell me where they are, right? So, and I might want to verify their location. So this can also apply to your other relatives or to work partners, or you might want to know that someone is connecting from a particular location and not from some location that you don't like. But then there are issues like location and identity privacy, and I'm not going to cover those in this talk because because it's a very, very difficult problem and we are not solving it. And I'm not even sure that there is a good solution to that problem. So what about GPS? Because that's the first thing that comes to people's minds. Well, GPS, at least civilian GPS, is not really secure. So what are the issues with civilian GPS? Well, you will see these research reports saying that GPS can be spoofed, that Iran managed to inject wireless signals and essentially mislead a U.S. drone to land in an Iranian U.S. airbase while the drone believed that it was flying to a U.S. base, right? Now, also some researchers from University of Texas also performed these kind of spoofing hacks on a U.S. drone with the permission of the U.S. Air Force. So how can you do these kind of attacks? Well, it's actually not really difficult. So you take these kind of devices that you see at the bottom of this slide that are called GPS signal generators. These are essentially test equipment which is able to generate wireless signals that correspond to the signals that the GPS satellite would generate, right? And now, if you are creative enough, now you can generate such signals that even if your GPS receiver receives legitimate GPS signals, you would still be able to shift a computed location to somewhere else. So, is this really feasible? How does this work? So here's the a little bit of James Bond background just for your entertainment, but this video shows you how this can be done. So this is a relatively simple example where we took a mobile phone and we essentially initially first calculated the location of this mobile phone where it actually is, and then we started spoofing. Yeah. And now the location actually shifted, right? As you see, right? We can shift the location to any arbitrary place on the planet. So you can see that we are now moving it at pretty high speeds. And now the next location that we are going to get will be in Berlin. And obviously the device didn't teleport itself to Berlin. So why does this work? Well, this works because if you think of a GPS receiver, it's essentially a receiver that's waiting for the outside information. It's a receiver, right? So it doesn't really transmit information. It's waiting for others to tell him where he is. So it's like me closing my eyes and just listening to all of you telling me where I am, right? And how is the location calculated? Well, it's essentially, you can think about it in the following way. So the satellites are transmitting their signals simultaneously, right, at the same time. And what the receiver is calculating is essentially a difference in the arrival times between different signals from the satellites, right? And based on these differences in the arrival times, it calculates its own location, and not only its own location, but also time. Because the clock of your receiver is not synchronized with the clocks of the satellites, and in order to compensate for that, we need at least 4 signals, and then the receiver is going to calculate its own clock offset to the satellites, which have atomic clocks, and therefore determine not only its location in 3 dimensions, but also the time, which is also fairly important because in a lot of critical systems like power grids and so forth, you're using GPS receivers in order to determine time, to close control loops. So if you would now spoof the time of these kind of systems, you could throw power grids out of control, and people have already shown that this can be done. So how do you spoof? Well, you can either modify the navigation signal message content, because these navigation messages, they actually carry some content, or you can manipulate the time of arrival. So this content, for example, can be where the satellites are. So obviously if you shift that, then you can shift the calculated location. Or you can manipulate the time of arrival, which is much more interesting because unlike the content, which we know how to protect in security by digital signatures, time of arrival we can't protect by digital signatures, because I don't care which kind of bits the message carries, but I care about the time of arrival. Now, if this is shifted, you have no cryptographic mechanism to detect this time shift. Okay? There's actually nothing that cryptography can do to help you to prevent this kind of a time delay. Okay? So civilian GPS is not authenticated and can be generated or delayed, but military GPS can only be delayed because they are actually authenticated through secret spreading codes. And I'll leave that for a more detailed discussion in case you are interested. Just to kind of inform you of the balance of the use of military and civilian GPS. Military GPS systems, they rely on pre-shared keys with all the receivers, because otherwise spreading cannot be done. And you can imagine what kind of a secret that is if you have to share it with many receivers, right? And so these kind of systems typically don't scale, and they're very hard to deploy. And that's why in a large percentage of military operations, civilian GPS is being used as well. And I would suspect that this is what happened with this Iranian drone as well. So how would you go about detecting GPS spoofing, right? Okay. So you can try to change GPS. So in some sense, you can try to say, well, I'm going to put some authentication on top of navigation messages, but this is not going to really help you because digital signatures in messages will just equally be delayed. You can also use secret spreading codes, which require shared secrets, and also that's not a perfect protection. You need to have a fair amount of environmental noise in order to hide, and someone who has good antennas can still dig these signals out. There are some ideas about delayed key disclosure. That's more for people who are in the area, right? That might hit a good compromise between these two, but are still vulnerable to some types of attacks. Or what you can do, you can try to look at the navigation signals that you receive, and you can try to detect that there is a spoofing by seeing, for example, there are too many navigation signals around, or that the noise level increased, or that or for example, that the number of satellites that are observed is unexpected for that location. Or you can look into autocorrelation peak distortions, spatial diversity in terms of where are these signals coming from. So, for example, if you detect that the signal is not coming from up in the sky, but that it's coming from some ground station or the direction of a ground station, you can try to detect this. So these are all kind of techniques that you can use in order to detect that something is off with the signals that you receive. There are a lot of, when you put this all in a box with some machine learning, there are a lot of false positives and false negatives that can hit you there. So your GPS receiver might go up and down in terms of signaling that there might be a spoofing attack. My point here is not to go over all these in detail, but just to give you an overview, right? I want to show you one particular attack, which we call a seamless takeover attack, because I think it illustrates how tricky these things can be and how subtle they can be. So here you see a ship in the middle of the ocean, and it's receiving satellite signals from legitimate satellites. And here's an adversary who will inject his own signals. So the adversary at first can transmit at a very low power, right? And he can transmit such that his signals are actually perfectly aligned with the signals from the satellites. This means that when you calculate what is called what is an autocorrelation peak, which detects essentially when the signals are arriving, then the signal of the attacker will be perfectly aligned with the signal of the legitimate satellite. Now, what does the attacker then do? Well, then the attacker will now increase the power of his own signal. And now the peaks will kind of flip, right? Now the stronger peak will be of the attacker, and the weaker peak will be of the legitimate satellites. And they're still perfectly aligned. Your location still didn't really change. And now in the third step, the adversary starts shifting a stronger peak away, shifting his own peak away from where you should be, meaning the attacker is now changing slowly your location. What will your receiver do? Well, it will start tracking the stronger peak, because that's how the receivers are built. And they will track a stronger peak, and they will ignore a weaker peak, because they will believe that that's a product of a multipath effect or of some randomness in the environment. Okay? And now this kind of a seamless takeover attack is just one example of how things can go wrong, right? And it's super subtle, right? Because it essentially eliminates the detection of signals which are injected by the adversary. There are many other things that you can do here. For example, you could be looking at the distortion of the autocorrelation peak, because here the autocorrelation peak is plotted with this perfect shape, but it's not going to have this perfect shape when you are in a real environment. So in order to kind of put all these things together and put many techniques together and to try to detect that spoofing is actually happening, what we have done is we started a small community project, an open source GPS receiver, which detects pretty much up to an accuracy all known attacks. So what have we done? We took essentially an existing open source GNSS platform, and we modified the acquisition phase of the signal and the tracking phase with some auxiliary peak tracking plus some detection and navigation message inspector to check for all kinds of consistency. And therefore, we strengthen this receiver with the detection module for, again, spoofing, right? We put in essentially a lot of techniques that were out there and that we came up with as well in order to build this system. Now, I'm not going to go over this, but just to give you an idea that this attack that we have that I just presented would also be detected using our techniques. So we would track, for example, all the peaks and then do some magic there to detect spoofing. It's open source. You can download it and use it. You can download the code. You can modify it. You can play with it. You can enhance it. You can do better results than we have achieved. We are still working on it, but it's really something that I believe in. What did we do in order to test our system? Well, essentially we generated our own GPS signals using GPS signal generators, the devices that you have seen. We also took some independent data. So there is a University of Texas spoofing battery, which they have a lot of data of different signals with spoofing, without spoofing, and so on. So we put those in as well. We did war driving around Zurich and around the Swiss countryside in order to collect GPS signals. And here, when I say we, the people who actually drove these cars and connected these USRPs and laptops were obviously my students who spent hours and hours of work doing this. So I cannot take all the credit, right? And then what we did, we fed all these into our system, and essentially we could detect all spoofing attacks that are aiming at shifting your device more than 1 kilometer away from its current location. And now we are working on getting this even tighter, right? Essentially, if you think about it conceptually, this means that a peak separation for this kind of a result can be clearly distinguished from multipath. Okay, so this is essentially one kind of a project where we are looking at how to detect spoofing using a single GPS device. However, we don't have to use a single GPS device to detect spoofing. We can leverage several GPS devices as long as we know their mutual as long as these devices know their mutual distance. So here's a very high-level idea. So imagine that you have a ship or a plane or a drone where you placed GPS receivers at different locations on the ship or a drone. And of course, these devices know that they are, let's say, 10, 20, 50 meters apart, because you put them there, and presumably no one moved them. So what happens if this spoofer here generates signals and tries to spoof these devices? Well, if you think about it a little bit, you will conclude that all the devices that receive the signals from the spoofer will essentially compute the same location. Now, why would they compute the same location? Well, because the devices are measuring the shifts, so the differences in the arrival times from the signals generated by the spoofer, and therefore, all these differences will be preserved because all the signals are traveling at the same speed of light, and therefore will resolve the same location. Now, this is great for us because we can therefore detect spoofing, because these devices, if these devices here all calculate the same location, then that means that spoofing is happening, because they shouldn't. They simply shouldn't. They are 10 plus meters apart. Okay, so this works up to a certain accuracy, right? But I think you can intuitively understand how powerful this is, because this means that now we suddenly have an upper hand against an adversary, right? As long as the adversary cannot selectively transmit signals into each of the devices. So now you can go a little bit academic and define this as a more general problem, a group spoofing problem, where an adversary has to solve this problem, right? And his problem would be how to place his spoofers. So now he can have multiple spoofers, and how can he generate signals such that he shifts an entire set of receivers in a certain formation to an entirely new location, right? Or any combination of these now. Yeah? So to give you an idea of some of the results, So what you can also now show is that if you have two receivers, what you are essentially doing, you're forcing each of the spoofers to sit on either a hyperbole or a set of hyperboloids or some intersections of these. So this means that as you increase the number of receivers that are in a particular formation, the problem for the attacker becomes more and more constrained. So the set of locations from which he can spoof becomes smaller and smaller, and eventually, after 5 receivers, you force the attacker to sit at the satellites in the sky in order to spoof. And then obviously that's game over, right? Because that's, if the adversary can really ride on the satellites, then the game is over. But that actually also shows that the technique is powerful, because that you assume that he cannot do. So yes, GPS spoofing can be prevented in a number of scenarios. However, if you really collapse this into a degenerate case of me being an attacker, putting a phone into a Faraday cage and feeding it signals, there is no way to detect spoofing. No way. Because I can always generate an environment for this phone that essentially corresponds to another location. Because there's no detection mechanism that can work in that case, right? Nothing works, right? This is this would be a Dolevial attacker. He can kill all the signals. He can inject whatever he wants. Nothing works, right? So, and this can be proven, right, relatively easily, that broadcast systems like GPS cannot fully secure against spoofing if the attacker controls fully the environment around the device. If the device, for example, mobile and moving around, and the attacker now has to move somewhere, then you can do something and detect spoofing. Otherwise, in this kind of environment, if I want to cheat on a GPS receiver in my own car, no help. Okay. So I could show that secure positioning requires either bidirectional communication or requires communication from the device to the infrastructure, but not from the infrastructure to the device, like we have in GPS. So either these two cases work, but the one that we have of GPS actually cannot provide security. However, it's a fantastic system because it provides global coverage, right? So not requiring bidirectional communication actually has its purpose, right? People who build it went for broad functionality, not necessarily for security. So if we now go back to Earth, where we can actually do bidirectional communication and put it in a context of, let's say, the fashionable world of IoT devices, then we can do secure positioning with 100% guarantee, and we can prevent any type of an attack. Okay, but we then have to use bidirectional communication. So why is IoT kind of positioning important? Well, I don't have to convince you, right? All of these devices, you approach your car, the car will unlock. You approach your laptop, the laptop should unlock. You approach your door, the door should unlock. You shouldn't be forced to press any buttons, to touch any sensor or whatever. Everything should just open for you, because that's what you want, right? We are lazy creatures, right? And we want things just to work, right? And the more you give us, the less we want to work. So, so I think this is really key, and it will be interesting in the future as well, right? Where also drones, when they fly around, they might want to measure their distances and therefore coordinate. So, I guess I already pretty much said these, but for payments, for pairing, for all kinds of applications, I think this is super important. So this is really intuitive, non-interactive approach to authorizing access to physical spaces or to data or to anything else. As I mentioned this scenario before, you want, when you enter a certain space, to be granted access to data, right? I think physical access control works pretty well today, right? So we can sort of keep people outside of spaces if we want to, right? And this is always the bottom line of defense, right? You put a guard there. If you are not comfortable with only a guard, you give him a gun. If not, you put 2 guards with a gun, and then you escalate further, right? So here's an example where this actually really mattered. So it's an attack that we did a while back. It's called, so the system that we attacked is called the passive keyless entry and start system, which is used to unlock cars. So these are the systems that you have most probably in most models, car models today. You keep your key in the pocket. When you approach the car will unlock for you. When you sit in the car, a little green button will light up, and you can press a button and the car will start, right? Everyone loves it. You don't need to find your keys, and everything is good, right? But how does the car know that you are close to the car? How does the car know that you are in the car in order to allow you access? Well, it measures a distance in some sense, right? It has to securely measure this distance. Imagine what would happen if someone would be able to trick the car into believing that the key is closer, that it's actually close, and then open the car and then start the car and drive away. So we didn't only imagine that, we actually did it. So this is a protocol that runs in most cars. Some use a slightly different frequency here, but roughly, there is an LF challenge that goes from the car to the key, from the car to the key, yeah, and which excites the key, and the key will then reply with an authentic reply. We didn't look into the crypto, we didn't look into this challenge response phase, we didn't change anything in the messages. A very simple thing that we did is we simply relayed these messages between the car and the key. That's all. And the car, my car back then, magically unlocked, right? As I was 60 meters away. So first we pulled the cable. We literally, this is the antenna that we use. So we literally, made a coil antenna in the lab and had a slightly larger antenna to excite the key from let's say 2 meters distance. So I could literally be now blasting the signals here into this room and relaying them to the parking lot and opening your cars, right? That's what one could do. But of course, it's really uncomfortable to drag these cables behind you to perform this attack, so we made it wireless. Of course, it was widely reported. Newspapers like this, people like this, because, cars are something that people are super keen on, and they can easily understand. Recently also, ADAC repeated this experiment. We did this in 2011. And they essentially went back and they said, hey, what about this attack? Does it still work? And surprise, surprise, in 2016, this attack still opens essentially all cars out there on the market. Does this happen in practice? Well, yes. So you see these guys that are essentially one with the device here. They are, what are they doing? So they're essentially exciting a key which is in the house, and then relaying the messages to the car, and then unlocking the car, starting the car, and driving away. So you come home, you put your keys on the table, your car is outside. I come with a colleague, I put the antenna onto the window, excite the key, relay to the car, start the car, drive away. Now you would say, well, what if the link between the key and the car is lost? Well, the car will not stop. The reason is essentially that, we all have kids. You have kids in the back seat, you give them the keys, they play, they throw them out of the window. Your car should still be able to drive to a nearby station, right? So, or to, in this case, to a disassembly shop. So, essentially, communication does not imply proximity in adversarial settings. This is something that is really, really, I know it's a simple message, but somehow people didn't catch that back then, and I've been pounding on it ever since, right? Communication does not imply proximity in adversarial settings. So we need to actually build a secure distance measurement system. So how do we securely determine that the distance between the two devices, or how do we securely detect the proximity between two devices? It doesn't have to be a precise distance, but it needs to be how do I know that I'm actually close to you within a certain distance, let's say within 2 meters, as opposed to hundreds of meters? And, it's relatively, that's what we want. And if you have never done radio design or wireless, you would say, well, measure some time and you'll be fine, right? Which is actually super tricky to do, and in the end the solutions go into that direction, but that's what we have actually done, right? So we have built this system. I will talk about it a little bit later. So what do we want? What is the security property first that we want? So what we want is we want that if we have A and B, this could be the car and the key, that are mutually trusted devices that have, keys pre-shared between them, because that's what you have in a car and the key, and a key fob. We want that the attacker cannot convince A and B that they are closer than they actually are. So we don't care necessarily about them being further away, because that's not interesting for access control in these cases at least. But we want, that's the minimum that we want, right? The attacker shouldn't be able to convince you that you're closer than you actually are. Okay, so how would you do that? So actually we went back, when we did all these attacks, and even before that, we went back to the past and we said, okay, did someone actually think about this? So there were works in 1993 by Browns and Chaum, and they were looking actually at this problem in a rather wired environment, right? They wanted to. There were so-called mafia fraud attacks, by which mafia would put out fake ATMs, fake money machines, right? And you would enter your card, and then you would enter your PIN, and this machine would then relay all the communication from to the real ATM, and obviously would have your PIN. And then the money would come out of the real ATM. Obviously, the attacker would get it, and you would get an error message saying, well, we are out of money, go somewhere else. Right? So it's a simple relay, right? I mean, because you would need to kind of recognize, so your card should recognize that it's close to the real ATM, right? As opposed to being in a fake ATM, right? So they started thinking, okay, how could we do that? So they proposed some protocols, initially called distance bounding protocols, and ever since we actually said, let's take that name. It's actually a pretty fitting name, and let's try to use these protocols. We couldn't actually use these protocols because they were built for wired communication, and there was no actually wireless system that could support this. And here's the reason why. Well, because if you try to build a secure distance measurement system, what would you initially say? You would say, okay, I need authentication and I need distance measurement. I will put them together and then this should be fine. So we tried, so you can say, I'm going to indirectly measure distance by observing receive signal strength, by observing phase. This is a multi-carrier measurement system from Atmel. We'll do it by frequency, by FMCW, right? Those are other types of systems. Or we can directly measure the distance by using chirp spread spectrum, by using essentially chirps, which are a special type of modulation that covers a wider spectrum. Or we can use ultra-wideband. There is already an ultra-wideband standard for distance measurement. So we said, okay, you can just take authentication, put that on top of these distance measurement systems, and then we're done. Well, guess what? None of these work, right? Because so they're all broken on many different levels, and it will probably take me quite a bit of time to explain why, but I'll give you a hint at one of the systems. But you can essentially count that all in red are broken. I can sort of firmly claim that none of the indirect distance measurement systems are secure, and that only direct distance measurement systems based on time of flight can actually be secured. Of course, if you consider like Dolev-Yao attack, right? If you weaken your attacker, then you can do something, maybe. So even standards, are not really fitting for this purpose, which is okay. They have not been built for this purpose. They have been built for distance measurement, not for secure distance measurement. So why are these broken? Well, because the attacks that we actually showed are not the attacks on the logical layer, they are attacks on the physical layer, right? So this is one of the simplest attacks. you transmit a signal, and based on the received signal strength, you measure the distance. Well, obviously, the attacker can put an amplifier, amplify the signal, and reduce the distance. So this doesn't work. Phase ranging, actually, you can play with the shifts in phases to take more time to explain, but it's a similar principle. You can roll over some phases. You can do many things. So this is what we did recently. We broke one of the Atmel systems by that was based on phase ranging, and showed that we can shorten distances arbitrarily, practically. But let me show you one attack, maybe that shows you the complexity of this, or better say, what are all the things that one has to consider. So it's called the early detect plus late commit attack, and it was, these guys from back then in Cambridge came up with it. So it's an attack where your ones and zeros are really are encoded in wireless signals, right? And they're encoded essentially as sequences of either sine waves or some particular modulation, right? Some shape. The symbols have certain shape, right? So let's assume that this is a symbol for 1 and this is a symbol for 0. What can the attacker do in this context? Well, what the attacker can do, he can actually start. So before the key. This is now a challenge. So this is now a signal that goes from the key to the car, right? So before the key actually starts sending a signal to the car, the attacker can start sending some gibberish to the car, and then when the attacker figures out which bit the key actually wanted to send, the attacker can continue with the correctly shaped symbol. Now, when the car at the end does the autocorrelation and tries to figure out which symbol it received, it's actually going to detect a 1, but it's going to detect a 1 with a time shift, with an earlier time than sent by the key. I know that this sounds a little bit counterintuitive, but you have to understand that the symbols have certain shapes and certain length in order to allow for channel properties to be taken into account, because you will never, so these signals will never look like this, right? They will always be somehow distorted. So actually detecting these kind of attacks might seem easy on this figure, but it's actually not, right? You cannot easily detect this. And we have shown this for many practical systems. So we show this, for example, for chirp signals, that this is easily done. I'll probably skip this. Another kind of attack on time of arrival estimation, which was done at EPFL, and it was done on 802.11 ultra-wideband ranging standard, right? It's called the Cicada attack. So, secure distance measurement actually needs to be based on direct time of flight and requires specialized physical layer design. And so we actually did that. We prevented relay attacks by short ultra-wideband symbols, where these kind of early detect late commit attacks cannot be done, where Cicada attacks are not feasible. We have a special modulation and time of flight scheme. We implement distance bounding protocols on top of it. We have some fancy stuff like distance commitment, which would take me probably a lot of time to explain now. So I'll skip it. And now when we put all of this together, we have a system that has these kind of characteristics. And one of my students back then, a couple of years ago, actually decided to start a company on this. And now after some years, we have a chip. So this is a chip with the antenna here, right? Which gives you secure distance measurement with round trip time of flight. These are the specifications, right? Very low power consumption, and the company is deploying this now in the new cars. So you will see this chip in your new cars. So of course, if it's our chip, it's going to be secure. If it's someone else's chip, I don't know. No. So this is just to give you an idea, right? The chip is very small. This is a development board. So this is just to give you an idea of how this really works in practice. So you can move around and get this is a distance in meters that's calculated on the fly. So we can really do it in real time, because the single measurement takes 1 millisecond, so you can literally do it in real time. Right? Now, why am I excited about this? Well, because, if you can prevent someone from reducing the distance between two devices, then you can actually enable secure positioning in a space. How can you do that? Well, there is a very simple argument, right? If you have infrastructure nodes, like these nodes here, that like V1, V2, and V3, this could be like your satellites, you know, the nodes that know their positions and they're mutually trusted. And now P wants to calculate its own location, right? Now, if an adversary tries to shorten the distance, he will be prevented by our system, right? So he cannot shorten the measured distance between P and any of these devices. So the only thing that he can do, he can try to enlarge this distance. Now, what will happen if he tries to enlarge this distance? Well, if he tries to enlarge D1, for example, he would need to reduce the size of D2 or D3 in order to make this new position consistent with this distance. And he cannot, because we can prevent distance shortening. So we essentially have a system for secure positioning that works within this triangle, right? And we don't really care if the adversary shifts you here, because, well, this is the space that our secure positioning infrastructure covers, right? So you know that if you calculate your location, let's say within the TU Vienna space, it's a secure position that you obtain. If your position is suddenly somewhere else, you don't care. You cannot say anything about its security, right? It might be fine, but you don't know if it's secure or not. So you have this very, very nice secure positioning system that you can build on top of this. Yeah. I guess this is a repetition. And now, of course, the vision, the grand vision that I have is that we can push this further, right? That we can now build systems that can expand this to kilometers and cover the entire cities and provide secure positioning within the cities, or at least larger spaces. And that's essentially a topic of my research in the next years, generously supported by the ERC Council. So I'm super excited about this topic. I mean, it's really something that I really, really like. I think it's an interesting interplay between security protocol design, radio design, physical layer properties, and there are a lot of things that one can do here, and I enjoy it. If you also enjoy it, please join us and do this as well. I think it's going to be incredibly important in the future for all kinds of purposes, authentication and so on. You can see all of them there, right? I don't want to throw in any more buzzwords. And I have one more, do I have time? A few more minutes. I have one more thing to show you, because I found it kind of complementary and exciting as well. So the surprising thing that came up, because in my group we were doing a lot of this kind of proximity-based things, is that at some point one of my postdocs and students, they said, well, maybe we can use something like this for online authentication, continuous online authentication. Like if you now approach your browser, can your browser or the server in a browser know that you are actually close to it? And could it provide you with like a seamless, continuous second factor authentication for online systems, right? Of course, we know how to do it. If I put my chip into a phone or into a laptop, I can do this. But can we do it within the constraints of existing browsers and phones? So we thought about it, and we came up with a system that I hope you will like as well. So we wanted to build really a continuous, non-intrusive, non-interactive authentication. So the main actually question here was that we wanted to say, if I approach my browser, and even without typing maybe I can type in my password, maybe not, but my second factor should be immediately engaged. I don't need to type in any pins, compare any numbers or whatever. If my phone is close to the browser, I should log in. That's what I want. And how did we approach it? Well, we essentially went on to see, how can we do this? So the phone would need to essentially detect if it's close to the laptop on which user is opening a browser session to the server, right? So somehow you would need this kind of a connection. So until actually recently, browsers were more sandboxed. Actually, recently Chrome started opening up Bluetooth a little bit, but until recently, there was no access to from the browser, so the script running in a browser couldn't really access Bluetooth or Wi-Fi or other interfaces, right? Because obviously for security reasons, right? You have untrusted code executing within a browser, it should be sandboxed. And what we also didn't want, we didn't want plugins, additional browser extensions, things installed on the system, right? We wanted that if you walk around the hospital as a doctor and approach any terminal, you are authenticated. You don't have to configure all this stuff. So the main design goal wasn't actually, we didn't start from the security goal. We started from usability and deployability goal, right? Which is usually a little bit, another way around it, right? We said, this is our primary goal, and let's see how much security we can obtain. And then we figured out, okay, but the only interface that's actually fully supported by all the browsers, and the interface that's natively supported on the phones is actually the microphone and the speakers. And so this is where we focused our attention, and we said, okay, let's actually have a phone and a server script check the proximity to each other by generating sound and by recording ambient sound. And this is natively supported. I mean, if you enable this feature, for example, this can be enabled per domain, right? So when you log into a domain, it will ask you once, do you want to enable this? You can make it permanent, or you can do it per session, whatever you want. But essentially, you enable every time Google, when you go to its page, and if you enable this, you enable them to record any sound that is in the environment, right? It's a little bit spooky, but people seem to like it. I don't know. So the basic idea is really, you enter your username, password, you transmit and record some sound. You do some comparison, right? I mean, again, not important, some feature matching and so on. You do some similarity score, some machine learning and AI, fancy stuff, as always, and then you send the login authorization to a server. Right? So you communicate to check proximity, and you record ambient noise to check proximity. So this is just a demo. One of my students is logging in, and just as a and then when he signs in, no interaction is required. The nice thing is that this works actually if your phone is in your pocket, if it's in the bag, essentially in the room. Of course, you could say, well, what if someone else is in the room? Yeah, sure. Then he needs to know your username and password, plus be in the room with you with that device. So that's our attacker model. We don't want, this is what we assume, right? We are talking about remote attacks, right? Not someone who is following you, right? Which I think in any case is a really, really strong attacker. So yeah, so that's pretty much it. So I really like this. If you're interested in soundproof, it's there as well. The guys are pushing on with it. I think it's a really cool project. We're actually testing it with 500 users currently, and it's probably one of the largest usability studies that I've seen. I've never seen someone so serious about user studies in an academic environment. So I really, and it's not me, it's my students. I really appreciate what they're doing. So obviously, acknowledgements in random order, because as I said, this is a lot of work, and I definitely didn't do all of this myself. There are a lot of people who now moved on to academic positions, industry, started startups and so on, that are working on these projects, and I absolutely have to acknowledge them. Obviously, there are a bunch of publications related to this, and I always have to thank ETH for providing me and these guys a wonderful environment for this research. So, and thank you for coming to the talk.
We have time for questions.
So it was either a terrible talk or such an amazing talk that no one wants to ask questions.
So one question: does the whether the distance is large or small, does this influence it? Like things that you design, so comparing distance measures in a room or a couple of buildings towards satellite, which is much longer.
So our distance measurement system, so currently, so the numbers that I've shown are a little bit even old, so they claim a range of 150 meters. The recent prototype should go up to 250 meters. Obviously, all of the numbers that I show here are line of sight. I think it was even, I have to state this because in a non-line of sight environment, it depends on the environment. So you have to always, you can never show, I mean, we have tests in different environments, but it's, you know, currently our system, let me give you maybe one example, is built in such a way so that it goes through a human. So if your key is in your back pocket, it can penetrate a human, right? It can go somehow to the car. So if that kind of communication is feasible. Now of course you can always increase the power if you want more of it, but these systems have to be designed such that they have a certain power within a certain spectrum. So you cannot arbitrarily increase the power because otherwise you will essentially jam everyone else. So you're not allowed, according to all kinds of US, European, and essentially global standards, to use arbitrary power, especially in ultra-wideband systems, which cover wide ranges, right? So of wide spectrums.
Okay, I have another question. Currently we have GPS, GLONASS, and Galileo, and we are about to have this Chinese and Indian satellite networks, and for sure soon every device will have a multimodal receiver. Is it any safer that, for example, the three-mode receiver will vote that if you spoof only the GPS signal, to remaining will outvote the spoofed one?
So other satellite systems, they operate in the same, let's say, almost the same way. Now Galileo is trying to push essentially secret spreading codes into the civilian domain, so allowing some sort of selective access to particular keys that are used to spread signals, right? So you need a symmetric key shared with the receiver, and then you spread the signal with that key, and then the receiver can be spread. And this is done essentially to provide additional resilience to spoofing, because if you can't find the signal, you can't shift it, right? So this would be the argument. However, it's not really clear. So the complexity of this deployment seems to be very high currently, because you know, who gives you this key? So this key needs to be given to you, and currently, as far as I understood, I've been looking into this a little bit, it will trickle down some national authorities and then potentially local law enforcements, and then you would get a key, and then you would be able to use it. So maybe if you are a transport company, you would somehow get access. But I've heard that the ideas are potentially that you would record your samples on your GPS receiver, send them into the cloud, and then they would return back a location to you, right? So that would be the kind of ideas that they're playing with. So it might be somewhat increased robustness, with a caveat, and my caveat is always that you are essentially assuming when you spread the signals that no one can find them, right? And the reason why no one can find them is that they are below a noise level, right? And that there is always noise, and that no one is able to dig these signals out of the noise, right? So let me give you a simple example. What if I point a satellite dish into the sky, right, into the satellites, and try to try to get these signals to be stronger, essentially increasing the gain of the to obtain the signals from the satellites, then in that case I will essentially reduce noise, increase the signal, and potentially can get these out, right? So, of course, it seems like a crazy type of an attack, but I don't want to say more, but let's say that we're hoping that it can work. Yeah.
You mentioned that some of the technology is going to be used in cars and other things. Can you talk about power consumption for these devices? How often you have to change batteries?
Sure. So you can. I'm actually super happy to talk about that because that's one of the main challenges for which the solution of that I can absolutely take zero credit. So we had to work there with people who are specialists in ultra-wideband low power radio design. Right, and these are the numbers. So essentially, the power consumption of these devices is roughly the same as low power or Bluetooth low energy, right? So this means in a scenario of a car key, so we can do 30 million measurements on a coin battery, because this key fob needs to last for four years roughly. And you can essentially on a coin battery that's how long it can last, maybe a bit more. So doing these systems to be with high power actually might not even be can be done, let's say, but doing it at such a low power and in the end building a chip that would work is quite a challenge, and was quite a challenge. Yeah.
I have something. Also a question that adds to the low power thing. Since it is such low power, is it still vulnerable then to jammers also? Because the signal strength is quite low, and if I jam the whole channel, then...
Sure, you can always jam these systems. This is not... pretty much there's no help there, right? I would say essentially jamming is a sort of a power game, right? Of course you can use spreading to do a little bit more, but in the end, jamming is a game of forcing the adversary to transmit at such a high power so that he would become detectable, right? And that you can pinpoint his location and take him out with different means, typically physical means, right? So because you can't do that, and here you're limited by regulations, right? You cannot transmit at a higher power than you are, and jamming here wouldn't really achieve much because it would just be a DOS. You wouldn't be able to enter your car. So fine. It wouldn't really matter, right? The system works in a way that when you approach a car, it will unlock. If there is no communication, it doesn't unlock. When you move away from the car, when it sees that there's no more communication, it can just lock itself up, right? For example. But there are different models of cars, and they handle this differently, right? Some of them require you to put a hand onto the lock, which is essentially just to somehow activate the whole process, right? But it's not really a security measure. It's more a, let's say, a convenience measure. There is also a lot of the psychology of the users, right? The users somehow prefer to have a feeling that they have actually done something for a system to unlock, right? They want to be able to do something, because then they feel like the system is more secure because they grab the handle. But it does nothing, right? Anyone else can grab the handle, right? There's no fingerprint sensor there or anything of that sort, right? So it doesn't really matter. Yeah. It makes people feel good, which I guess it does something, yeah.
Having been interested in infrastructure-less device-to-device authentication for a couple of years, I've asked Srdjan again, so I guess this is a question somewhere between Srdjan and Nick. What would it take for us to get this in Android devices for them to authenticate among each other?
Hey,
how far are we away from that?
Hey, when can we start? No, of course, having these kind of things deployed in phones and so on would be simply fantastic, for in general. But it's more a decision for companies to say, hey, this is something that we can use. We have been talking to some companies that manufacture phones, and so we are hoping that something might happen. I'm kind of convinced that maybe not if not in the next 5 years, but in the next 10 years, there will be an ultra-wideband distance measurement technology in the phones. Is it going to be exactly this kind of a system or slightly different? I don't know, but I'm convinced that one will be there, not only for security, but for many other applications. So, hey, this is something that we put out there. If someone is interested, we are super happy to deploy it, right? So that's a bottom line. We are actually working on, Mac layers for this and all kinds of other things. And in this play of standardization and companies pushing for deployment and things emerging through different channels, it's hard to predict how much one can influence. The only thing that I can do is give these kind of talks and try to get people excited about it. Yeah. But thanks for the question. I think it's great.
Thanks, and I think it was also a great last question. Thanks again for your presentation, and let's go for a coffee break.